Well, hello, good people. Today we are talking about gravity. Now, some of you have heard the story of how Isaac Newton discovered gravity when he was sitting under a tree and an apple fell and hit him on the head. And I say, no, that can't be at all how the story went, because if an apple fell and hit you on the head, it wouldn't give you a great idea. It would give you a concussion. And so I say that is not at all what happened. No, what happened must have been that an apple fell, and it fell right down on the ground next to Isaac Newton. And he must have picked up that apple and said, oh, wow, look, a snack. Buffed it on his shirt, went to take a bite, looked and saw that there, poking a little head out at him, was a little worm with a little smile on its face. And I imagine Isaac Newton looked at that little worm with a little smile on his face, and disgusted and shocked, he took the apple and he threw it as far as he could. Now, here's what happened when he threw the apple. That is when the moment of genius struck him. That is when he discovered what gravity was really, really like. Because here's what happened. Isaac Newton threw that apple, and when he threw it, he saw that that apple followed a curved path. I'm going to draw some planet Earths. One moment, please. Here is an Earth. Here is another Earth. Here is another Earth. Okay, not too bad. We got 3 Earths. Here's what he did. He took an apple, and he threw that apple. And when he threw the apple, that's a terrible apple. That looks way more like a piece of popcorn than an apple. So sorry. I am just going to try one other time, and then I'll be done trying with my apples. Okay. Here's the apple. He threw the apple, and what he saw is that when he threw it, this apple followed a curved path down towards the ground like this. And he thought, well, that's interesting. He said, I wonder what would happen if I threw it a little bit faster. Because he said, I know that if I throw something, it follows this nice curve. And it always seems to follow that nice curve. But what if I threw something a little bit faster? Like if I had this apple here. Oh gosh, I'm going to have a piece of popcorn apple again. Okay. If I had this apple here, and I threw it, he said if I threw it a little bit faster, it would stretch out the curve. And that apple, instead of going and landing here, if I stretch out the curve, it might land over here. He said if I threw it fast enough, it might be able to curve around the Earth and land in another country. He said if I threw it even faster than that, well, I could stretch out the curve even more. And maybe if I could throw it even faster and I could stretch out that curve even more, well, then maybe it would land over here somewhere on the opposite side of the world. And then he said, what if I took that apple and I threw that apple so fast? Wait, we can draw an apple. Okay, that's not like the best apple, but that's not too bad. He said, what if I threw it so fast that it actually stretched out the curve so much so that it never landed on the Earth? He said, then that apple would probably come back around the whole Earth and hit me on the back of my head, and well, at that point, I would most definitely have a concussion. He said, but if I stepped out of the way and I wasn't there, well, then the apple would probably just go around in the circle again, and go around in the circle again, and go around in the circle again, and it would never actually get to the place where it falls and hits the Earth. And he says, you know, that's so funny. That's like exactly like what the moon does. He said the moon is very similar. The moon goes around the Earth like this. Never falling into the Earth and also never going past. Now he says it must be that the moon is just like a thrown apple. Those must be the same. It must be the same rules that govern them both. Now he says it must be thrown at the moon must have been thrown past the Earth at the very, very perfect speed. Because he says, I know what would happen with an apple. If I threw an apple too slow, well, too slow of an apple would land on the Earth. But then he said, I could also probably throw it too fast. And if I threw it too fast, it would go all the way off the Earth and it wouldn't actually even make it all the way around at all because it would just keep on going on its merry way. So he said the moon must have been thrown at the perfect speed to just make it around the Earth and keep orbiting around the Earth. And this was his brilliance. Isaac Newton did not discover gravity. People before Isaac Newton had been living on the Earth and they knew about gravity. It wasn't Isaac who said, yes, I have a theory that if you drop something, it falls because of gravity. That was not a new idea. Everybody before that knew that if you drop something, it falls. Everyone knew that. But what happened, his idea was that the same thing that makes apples curve towards the earth is the same thing that makes the moon orbit around it. And that was his brilliance. He took two things that were seemingly separate ideas, and he said, what if these two separate ideas are actually not separate ideas? What if these two separate ideas are really deep down caused by the same thing? And so many of our advances in physics have been like that. It has been that we had two things that seemed like separate ideas, like electricity and magnetism, but then we combine them together and we say, well, actually, maybe they're caused by the same thing, and we call that electromagnetism. So this was Newton's genius with gravity, is that he said, what if you have these two things that seem separate, an apple falling in a curved path towards the ground and the moon circling around the earth, and what if they are really deep down caused by the same thing, which is gravity? This led Isaac Newton to say that there must be some force that pulls together every object with mass. And that's what gravity is definitionally. Gravity is a force of attraction. That's a really terrible A. A force of attraction between any objects with mass. Gravity is a force of attraction between any objects with mass. Now, gravity is one of our 4 fundamental forces. We have talked about a lot of different types of forces in this class. We've talked about the force of tension, we talked about the force of friction, we talked about the normal force, we talked about the force of gravity, and those are all different types of forces. But we say in physics that if you could zoom in on each of these types of forces, you would see that all of these different types of forces really just boil down to 4 main forces. And so every force can be categorized into one of these 4 categories. These are the 4 fundamental forces, and here's what they are. The 4 fundamental forces, the forces that make up every other force on the planet and in the universe. Whoop. The 4 fundamental forces are as follows. We have gravity, which is our topic of the day, and is that force of attraction between any objects that have mass. We have the electromagnetic force. Electromagnetic force. That's the force that you have between 2 protons that pushes them apart, a proton and electron that pulls them together, an electron that pushes them apart. It's a force between charged objects. It's that force between positives and negative charges. The 3rd fundamental force is what we call the nuclear weak force. And the 4th fundamental force is what we call the nuclear strong force. Now, the nuclear weak force and the nuclear strong force you don't need to know much about. We'll get to it when we talk in Unit 12. In short, the nuclear weak force is responsible for a type of decay called beta decay. It can turn a neutron into a proton by changing one of its down quarks and turning it into an up quark, but that's way more than you need to know for right now. All that you need to know is that it's something that happens inside of protons and neutrons. The nuclear strong force, that's the force that holds protons together, that glues them together, or holds protons and neutrons together in the nucleus of an atom. So it holds together the neutrons and the protons in the nucleus, and that is the nuclear strong force. Of these 4, the way that we have listed them now, from 1 to 4, this is in order of weakest at the top to strongest at the bottom. You got to know that the nuclear strong force is the strongest force because it has the word strong in it. So that makes it probably a pretty strong force. The nuclear strong force is the strongest. Gravity is the weakest. Gravity is such a weak force that if I take 2 protons and I stick them next to each other, I'm not even talking about the gravitational force between them. Why? Because it's so negligible. It's not even worth noting in our conversation. The electromagnetic force, that is totally worth noting because there's an electromagnetic force that is trying to push those 2 apart. The nuclear strong force, that is absolutely worth noting because there is a nuclear strong force that is binding those 2 protons together, holding them tight in the center of a helium atom. But it is not even worth mentioning gravity because the gravitational force between those 2 protons is so negligible, it's not even worth talking about. So gravity is the weakest of the 4 fundamental forces. I also ask students in class, I ask them, hey, which one do you think that we know the least about of these four? And the one that we know the least about is gravity. We know that every mass pulls on every other mass. But if you were to ask a physicist, why does all matter pull on other matter? A physicist would say, I don't know. We have some thoughts as to some reasons why that might be happening, a few different theories. We will talk about, basically, Einstein talked about the bending of space-time. So if you have something that has mass and it exists in space-time, it'll bend space and time, kind of the same way that a bowling ball would bend a trampoline surface. So then anything that happens to come wandering by will then follow the curve of space-time and end up wherever that object is. So that's one idea, is that mass bends space-time, and that's why all objects that have mass get pulled together, is because they're following the curve of space-time. Another idea is that there are these little particles called gravitons, and a graviton is a little particle that anything that has mass has a graviton. And different things that have mass, what they'll do is they'll take their little graviton particles and they'll throw them back and forth between each other. And that exchange of particles, the toss back and forth, is somehow bringing them closer and closer and closer together. So that's another theory. We also have theories about gravitational waves that are emitted by every object with mass, the same way that something that has light would emit light waves, something that has mass would emit gravity waves. So those are all kind of working theories right now. But the truth is that we don't have anything that's really super satisfactory where we're putting our feet on really solid ground when it comes to gravity. We have done some great work in quantum mechanics where we have an equation that pretty much describes all of reality. And you know what force we can't fit into that equation? Gravity. Every other force fits very neatly and nicely, and it all looks very, very nice. But we do not have a current system right now to talk about how gravity fits into that whole system. We just don't have it. So gravity is the one that doesn't seem to fit with all of the other ones. Forces 2, 3, and 4 we seem to know a little bit about, but gravity just doesn't seem to fit with the other three. So that is the one that, surprisingly, even though that's the one that probably impacts your daily life the most, it's the one that we actually deep down on a fundamental level know the least about. Now, gravity is this force of attraction between any two objects with mass. And we mean really any objects with mass. So right now, I have a force of gravity that is pulling me towards the desk that I'm sitting in front of. And I also have a gravitational force that is pulling me towards my car that is in the parking lot right now. And there is a gravitational force pulling my pen towards my piece of paper. That is a gravitational force that is happening in the real world right now. So all of these forces are gravitational forces. There is a force of gravity between anything with mass. Now I'm going to show you a video here of what we call the Cavendish experiment, and I'll kind of show you, I'll give you this like YouTube link so that you could take a look at it, because I'm going to try to play it on here, but it might be laggy as things are when you try to record videos with them. So I'm going to try to show you this video here. And I'll also give you the YouTube link for it if you want it. Please let me know and I can get that for you. But I want to show you this experiment called the Cavendish experiment. Let me get it pulled up here really quick. I'm going to go ahead and pause the video, get it pulled up here, and then we'll be right back. One sec. Okay, so here's what you're going to see. This is the Cavendish experiment. Now, this Cavendish experiment, it's been performed thousands of times, and you could actually probably do it at home, except that you would need a place that's very, very still and not being affected by a lot of motion. But here's the idea. This is just a physics teacher who's doing it in his classroom. He has a meter stick set up like this, and then he has some masses taped onto this end and some masses taped onto this end. What you can't really see very well is that this meter stick is being held by a string right here. It's being held up towards the ceiling, so it's attached to the ceiling, and it's just dangling down so that this meter stick can kind of rotate around and can kind of swivel. Now what he's going to do is he's going to put a bowling ball right here and a bowling ball right here, and then we're going to watch a little like time-lapse video here. I'm going to get my face out of the way. We're going to watch a little time-lapse video here so you can see the clock down in the corner. And this time lapse is going to show us what happens at a faster pace. So we'll go bowling ball here, watch what happens. Here we go. Okay. Now it's perhaps a little bit laggy, but what you should be able to see here is that these masses moved towards the bowling balls. Why? Because of gravity. There is a force of gravity between these masses and the bowling balls. If you set those two bowling balls next to each other on a frictionless floor and you just let them be, those two bowling balls would slowly slide towards each other. That's inevitably what would happen because there is a force of gravity between any objects that have mass, and you can see that here in this video. I'm going to pause this and navigate us back over to our other page. 1 second, please. Now, if you wanted to talk about the strength of the gravitational force between the bowling balls and the masses, here's an equation that you could not use. You could not use Fg is equal to, wow, that's a terrible Fg, but you get the idea. You could not use the equation as Fg is equal to mg. This is the force of gravity on an object of mass m while it is on a planet that has an acceleration due to gravity g. So that would be something like the weight of an object. It's how hard the Earth pulls on an object. If this value here is 9.81, it's how hard the Earth would pull on an object of mass m if it was on the Earth. That is not the same thing as how hard the bowling ball pulls on the mass. That's just not what that equation can do for us. So that is just really bothering me. It was just such a poorly written letter F. Okay, that one is got even sadder somehow. What in the goodness? Let us try again. Or maybe not. Maybe none of this is worth it. You guys are like, this is not worth it. I know it's an F, and then we can move on. I know, but I just care. I care for some reason. Okay, better. Now, if we wanted to look at the force of gravitation between the bowling balls and the masses on the end of the meter stick, we would need a totally different equation. And the equation that we would need for this to find the force of gravity between them is what we call the law of universal gravitation, or the universal law of gravitation. You can say it either way, it is great. The law of universal gravitation or the universal law of gravitation. Either one is great. The reason why we say universal here is because universal means this equation can be applied to anything. This equation only finds you the force of gravity acting on a certain mass while it's on a certain planet that has an acceleration due to gravity g. This equation can help you find the force of gravity between any two objects with mass. And this equation looks like this. It's capital G times the mass of the first object times the mass of the second object divided by the distance between the centers of those two objects squared, where r is the distance between them. M1 is the mass of the first object, M2 is the mass of the second object, r is the distance between the centers of those two objects. And this is, of course, an equation that is most definitely worthy of your bag of tricks. You could use this equation to calculate the gravitational force between the bowling ball and between the masses on the end of the meter stick. Here, this value g is a constant. It's called the universal constant of gravitation, or the universal gravitation constant. Either of those are totally fine. The universal constant of gravitation is a constant that is in this equation always, and it is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. Now, this number, you'll notice here, is a tiny number, which reflects back on what we said about gravity being such a weak force. Do you see how with a tiny number, like a times 10 to the negative 11th kind of number in here, you would need a lot of mass here or a lot of mass here, or you need them to be very, very close together to even make a number that is even a noticeable kind of size. In order to overcome this times 10 to the negative 11th, you need a huge mass and a huge mass, and you need a relatively small distance between them in order to have kind of like a normal number here. So, is there a force of gravitational pull between your pencil and your paper? Yes, but M1, the mass of your pencil, and M2, the mass of your paper, are so small that you really can't tell what the actual force between them is. That's not something that you can see, especially when you multiply by this 10 to the negative 11th. So that shows you that this really is a kind of tiny force. Now it should make sense to you that we have masses in the top and the distance between them in the bottom, because you know that if two masses are bigger and bigger and bigger, the bigger those masses are, the bigger the pull of gravity between them. And if those masses are smaller and smaller and smaller, the less that mass is, the less the pull of gravity between them. It should also make sense to you here that there's an r in the denominator. Why? Because as things get further and further and further apart, the force of gravity between them gets weaker and weaker and weaker. You know this because as you leave the Earth, you know that the force of gravity acting on you as you get further and further and further from the Earth is less and less and less. So it should make sense to you that you've got mass in the top and the distance between those masses in the denominator. Now, one mistake that some people will make is some people will say, yes, Miss Wilson, I got G. And G. Same. No. These are super, most definitely, most absolutely, most certainly not the same thing. Lowercase g is not the same thing as big G. Big G is the universal constant of gravitation. It applies everywhere in the whole universe all the time. It is, you could use it for any two masses that are being pulled together, and you would have to use it in the context of this equation. G is the acceleration due to gravity on a specific planet. On Earth, it's 9.81 meters per second squared. But that's not G everywhere. That's just G on the Earth. If you went to Saturn, you would have a totally different value for G. And if you went to the moon, you would have a totally different value for G. So where you are changes what G is. G is the acceleration due to gravity on a specific planet or near a specific body of mass. If you wanted to calculate G, you could totally do it. Here's what you would say. You would say, well, the force of gravity that acts on an object that's near a planet would be the mass of that object, we'll do mass of O for object, times G, that's the acceleration due to gravity for that specific planet. And that would equal, well, because this is the force of gravity, that's how hard the planet pulls on the mass, that's also going to be this force of gravity. That would also equal G times the mass of that object times the mass of that planet divided by the distance between the center of the planet and the center of the object. If you got an object on the surface of a planet, then the distance between the center of the planet and the center of the object is most likely just the radius of the planet squared. If I solve for the G on that planet, notice the mass of my object would cancel out and I would be left with, let's move this away. Go. Wait. Yes. Oh, wow. I can't believe you did it. Okay. We would be left with the acceleration due to gravity on that planet is equal to G times the mass of that planet divided by the radius of that planet squared. Notice that the object is not at all a part of the equation. The acceleration due to gravity on a planet depends on the planet. It doesn't depend on who is there on the planet to experience it. The acceleration due to gravity on Earth is 9.81 meters per second squared. That is true if you are here, and that is true if you are not here. That is true if it is pulling on a pumpkin. It is true if it is pulling on an elephant. It is true if it is pulling on a feather. And it is true if it is pulling on nothing. The acceleration due to gravity on Earth is always 9.81 meters per second squared, regardless of who is there to experience it, because it only depends on the mass of the Earth and the radius of the Earth. And that doesn't depend at all on the object that is experiencing it. Do add this equation to your bag of tricks as well. Oh no. Okay, that's a little bit better there. Now here's a question for you. Suppose that I said that you were going to travel to the planet Zorbo, where we know that the mass of the planet Zorbo is, let's say, twice the mass of Earth. And we also know, of course, that that the radius of the planet Zorbo is a third of the radius of Earth. Here's a question. How many more times would you weigh, or how many more times less would you weigh on, how many more times less? That's what I said. How much more or how much less would you weigh on the planet Zorbo in comparison to your weight on Earth? Well, here's what you would say. You would say the acceleration due to gravity on the planet Zorbo is going to equal G times the mass of planet Zorbo divided by the radius of planet Zorbo squared. And then you would say, let's move my face out of the way, classic. And then you would say, well, I know that the mass of planet Zorbo is 2 times the mass of Earth. I know that the radius of planet Zorbo is a third of the radius of Earth. And then you say, okay, let's take a look at what this means. This means that G on the planet Zorbo has to be 2 times bigger, at least, because we got a G times an ME up top, and that the mass was 2 times as much. So it's got to be at least 2 times bigger than regular G on Earth. And then we have a 1/3, but it's squared and it's in the denominator. The 1/3 being squared means that this is really a 1/9 in my denominator times RE squared. Notice here that this G mass of Earth over the radius of Earth squared, we could just rewrite that and say that that is, 2 over 1/9, isn't that just the G on Earth? But now we got a 2 divided by a 1/9. A 2 divided by a 1/9, well, we could just flip this up into the numerator, and we would get that G on the planet Zorbo is 18 times G on Earth. That would mean that you weigh 18 times more on the planet Zorbo, and you would accelerate 18 times faster on the planet Zorbo than you would on the planet Earth. So what you can see here is that your acceleration due to gravity, or we also call it the gravitational field strength, but your acceleration due to gravity depends on the mass of the planet and the radius of the planet. If the mass of the planet increases, the acceleration due to gravity increases. If that planet is more dense, if it has all that mass concentrated into a smaller amount of space, then the acceleration due to gravity is also greater. One last concept for today, and that is a concept that I like to call earth diving. You know, when skydiving was all the rage, well, that was before they drilled a giant hole through the center of the Earth. Suppose that for your, wait, I don't want the color purple. Goofy, give me green. Okay, suppose that for your 18th birthday, your parents have bought you earth diving tickets to allow you to go earth diving through the center of the Earth. When you go earth diving through the center of the Earth, as you know, oh gosh, that was supposed to be an eraser, and it just was not at all an eraser. Come on, go away. Go away, you can do it. Are we processing too slow? Okay, here we go. Okay, let's suppose that there is a giant tunnel through the center of the Earth like this, and that this giant tunnel allows you to go through the center of the Earth. Oh no, oh, this is gonna be bad. Okay, actually, I'm gonna pause this video, I'm gonna draw it, and then we'll talk about it. 1 second. Okay, here we go. You are going to fall through the Earth like this. So they have a giant tunnel through the center of the Earth, and this giant tunnel, we'll say that it is like reinforced and that it's not going to collapse back together, and we'll say other goofy things like, well, let's say that there's no air resistance in this tunnel and that kind of thing. But you are going to go through this tunnel, and what's going to happen is you're going to take 1 foot, you're going to step off, and then you're going to start falling through the hole. And now here's our question is, what's your acceleration and your speed going to be like along this whole journey? We're going to go point by point. First, we're going to talk about our acceleration, and then we'll talk about our speed. At first, when you first step into this hole, your acceleration is going to be equal to the acceleration g, and it's going to be pulling you down. And the reason why is because that's basically like being on the surface of the Earth, and so your acceleration would be g. When you get to this point here, your acceleration will now be less than g, but it will still be pulling you down. There's a reason for that. Here's why. A lot of students say, but Miss Wilson, wouldn't you be closer to the center of the Earth, so then wouldn't that make it so that your acceleration is more? No. Oh gosh, it always does this. Please don't do that. Goodbye. Okay. No, actually your acceleration will be less, and here's why. Is because you are getting closer to the center of the Earth, but right now you have this much, oh, that was not good, but it's okay, we're doing it. You have about this much mass from the Earth underneath you on this side, and then this much mass from the Earth underneath you on this side. Okay, so you have this much of the mass of the Earth underneath you, and above you, you have, wait for it, yeah, gosh, no, not that, please, don't do that, please, and thank you. And above you, you have, wait for it, yellow, what a great color, okay, you have this much of the Earth above you. So, you have this much of the Earth underneath you and this much of the Earth above you. Well, that means this much of the Earth is going to be pulling you down. But at the same time, this much of the Earth is going to be pulling you back up. And so there will be a war between the bottom half of the Earth and the top part of the Earth. And the bottom half of the Earth would say, go down, accelerate down. And the top half of the Earth will say, accelerate up, accelerate up. But at this point, actually, the bottom part of the Earth will win because there is more mass below you than above you. But because some of the Earth is pulling you back upwards again, your acceleration will be slightly less than g. Less than g because there's a battle. Not all of it is pulling you down, only part of the mass is pulling you down. And so that's why your acceleration there will be less than g. When you get to the dead center of the Earth, so that you are exactly in the middle, your acceleration at this point will equal 0 because half of the mass will be above you, half of the mass will be below you, so you will be equally pulled up and down, so you'll have no acceleration at that point. Then, when you get down to this point here, now, instead of having acceleration that's pulling you downwards, now your acceleration will pull you upwards because more than half the mass is above you and less than half the mass is below you. So in the war between them, the top half of the Earth or the top part of the Earth will win. I keep saying half. I don't mean it really half, like a literal half. I just mean the top part of the Earth will win and the bottom part of the Earth will lose. So it will start pulling you back this way. When it starts pulling you back that way, it's going to pull you with an acceleration less than g because it wants to pull you. It's not going to pull you with an acceleration of all of g because it would take all of the mass of the Earth to pull you with an acceleration of all of g. So it's going to pull you with an acceleration less than g because we have less of the mass of the Earth and some of it's pulling you up and some of it's pulling you down. Now, then when you get out onto the other side, your acceleration now is going to equal g because now the whole Earth is going to pull you again. But this time the whole Earth is pulling you up. Let's talk a little bit about your speeds in this situation. You would start when you first step into the Earth. Your speed at first would be 0 meters per second. But then as you fall, you're getting faster and faster and faster because the acceleration is downwards. Now here your acceleration is less, but it's still downwards, so you're still getting faster, 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 faster until you get here. At the center of the Earth, your acceleration is 0, which means you're not speeding up, you're not slowing down, but you're also not at rest because you already have some velocity. So you're going to keep on coasting through the center of the Earth, get it at the same speed, and at this point you're just going to coast at a nice constant velocity until you get over here. When you get over here, now the acceleration is less than gravity, but it's pulling you back up. You're going down, the acceleration is up, so as you go down but the acceleration is up, you are going to slow down, slow down, slow down until you get to here. Once you get to here, the whole of the Earth is pulling you back up. And at this point, you'll have a speed of 0. So now you have a speed of 0, the whole of the Earth is pulling you back up, and you'll start to move back up again. When you move back up, now you have acceleration pulling you up, so you're going to speed up, speed up, speed up, speed up until you get to the center. When you get to the center, you'll have an acceleration of 0, so you'll coast on through the center. But then now gravity is pulling you back down predominantly, so the acceleration is predominantly down, but you're going up, so you're going to slow down, slow down, slow down, slow down until you get to here, and then your speed is going to be 0. But then the whole of the Earth is pulling you down, so then you're going to speed up, speed up, speed. Did I say slow down? I meant slow down, slow down, slow down until your speed is 0. Then here your speed is 0, you're going to start to fall back down again because gravity's pulling you down. So you're going to go faster, 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 coasting, slower, 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 0, then faster, 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 coasting, slower, 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 0, faster, 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 coasting, slower, 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 0, and you will go back and forth and back and forth and back and forth, and that will be the adventure of a lifetime. And I really do mean the adventure of a lifetime because that is what you would be doing for the rest of your lifetime. And that is all for today, folks. Today we talked about gravity. We talked about what gravity is, how gravity is the same thing that makes apples fall as what makes the moon go around the Earth, and that was Isaac Newton's great discovery. Then we talked about how there are 4 fundamental forces. Gravity is the one that is the weakest and the one that we know the least about. We talked about how gravity is this force of attraction between any objects with mass, which literally does mean any objects with mass, and you can use the universal law of gravitation to calculate the exact magnitude of the force between any 2 objects with mass. And then we talked about how you could find g on different planets. That's the acceleration due to gravity on that specific planet. Those two equations are very similar, by the way. Make sure that you know the difference between them. Then we talked about how would your weight be different on a different planet where the acceleration due to gravity was different. And finally, we ended by talking about what would happen if you were to fall through the center of the Earth. What would happen to that gravitational force of you if you were inside of a planet? And that is all for today, folks. I hope you do have a wonderful rest of your day, and I'll see you all next time. Bye, good people.